Number 15. We have a reaction, we have a rate law, and actually there's some important information in this rate law. You notice that it's second order with respect to A, and they're asking us which graph would best represent its change in concentration over time. And so let's do a little reminder of graphs. Whenever something is, you remember you can plot the concentration of something over time and get a straight line. If you get a straight line when you're plotting those two things, then it is definitely zero order with respect to A. If you plot the same thing and you get a straight line when you do natural log of A versus time, then that tells you that it's first order. And of course you do the same thing, plot 1 over A versus time, and if it's straight, and usually they're straight like that, it's second order. So the thing that I'm going to remind you is if it's first order, you might wonder, well, what happens if I just plot concentration of A versus time? If it's first order, we know it won't be straight like it was for zero order. It'll kind of be a curve that goes down like that. So you obviously can plot it, it just won't be linear. If it's first order, you'll get a linear plot like that. And same goes with these other ones. If it's second order with 1 over A, if you were to plot concentration of A, it would look like that, and if you were to plot natural log of A, it would still be non-linear. So since ours is second order, we think it's going to be 1 over A versus time, not Tim, time. And so I think D is going to be the correct answer here. Number 16. After 44 minutes, a sample of this stuff. First thing to note right here is really important, is that is a radioactive isotope that is decaying. It's a nuclear decay, and you remember when radioactive isotopes decay, it's always a first order process. There are no exceptions to that. So it's not really a reaction, it's more of a nuclear reaction. And they like to use these cases because they're always first order. And so you're supposed to know that's the key piece of information here. And so, if you think about half-lives, a lot of times it's nice to think in terms of time and amount of material left and sort of make just a quick chart for yourself. They said that after 44 minutes, 25% of it remained. So in the beginning, at time 0, we had 100%. I guess it's minutes. We had 100% of our material remaining. And at some time later, we had 25% of it remaining after 44 minutes. And you can kind of fill in the table from there, right? So if you go back and you say, well, how long would it have taken me to have 50% less left? Well, the answer is 22 minutes. And this seems super obvious, but remember, this sort of regular decay pattern is a hallmark of first-order kinetics. And isotopes always use first-order kinetics when they decay. So I think your answer is going to turn out to be, let's see. I was reading the question. They want to know the half-life. The half-life is the amount of material it takes for the amount of time it takes for half the material to disappear, and the answer appears to be 22 minutes.